Okay, so I'm Avneet. I joined this year, at the start of this year, at University of Bergen. I work with Francois and Alberto on strongly coupled DA. And I'll be presenting something that I've been working on for the past few months with a toy model. So it's kind of an introduction for me to the field of DA because I come from a different background in physics. And I hope you get to enjoy it as much as I did. So the motivation for this, my project in general, is to come up with a strongly coupled DA scheme, mostly for a system which have more than one component, and these components are evolving at the different temporal and spatial scales. So this kind of makes the intrinsic process of DA a bit more complicated than what we are usually used to seeing in a single component system. To formulate this process, I will start by just telling you that I'll consider a model where there are two components in the system. One is the ocean, one is the atmosphere, and there will be some macroscopic physical properties of the system will be covered. And the strongly coupled DA in this case simply refers to the normal DA that you usually like the theoretical implementation of DA, where the error covariance matrices have non-zero off-diagonal terms. Usually when you have just one component, you just have the variance of the component on itself, so you don't have the cross components. But if you have more than one components, then the cross covariance kind of comes into the picture. And like I said, when your subcomponents are evolving on a different, for example, temporal scales, then the time stepping of DA actually depends of the optimal time stepping of your DA procedure depends on both on the ratio or, for example, the combination of both the temporal scales. To apply a process, a strongly coupled DA to a system with components which are evolving on different time scales becomes not as easy to optimize. So this is the basic goal, to optimize this process. And to start, I will consider a simple toy model in which my state is defined by the temperature anomalies in the ocean and the atmosphere. And this model is simply defined by this linear equation in T, where the nabla here is a so-called translation operator in time. It has all the d by dt's, and there's m here in front of the ocean component, which basically means this controls how fast or how slow the ocean is going to move with respect to the atmosphere. Usually the value of m is larger than 1, which basically means that the ocean is moving slower than atmosphere. And then you have a stochastic forcing term, which is only contained in the atmosphere, just to keep things simple and straight. It doesn't actually matter. You don't have to put stochastic term in both because the model is coupled. So any stochastic input on one side will eventually be transmitted to the other side anyway. And the C here is simply a matrix with a 2x2 matrix with all the terms are here are constant. So this gives you a simple a linear model with a stochastic forcing and with a temporal scale separation. So basically I have all the basic ingredients that I need in the model to tackle the problem at the 0th order, at the simplest possible level. So like I already said, the model is linear in T, and it's kind of quasi-stable, which is to say that in the absence of the stochastic term, your final solution just tends to 0, but if the F term is actually not 0, then the system is kind of kept alive by the stochastic forcing term at all times. If you actually calculate the LE in the limit when F goes to 0 of this model, you will easily find out both the eigenvalues are negative when the matrix C is a positive definite, and which kind of implies that both the LEs will also be negative, so the system is fully stable, no chaos, very simple system. So nothing very surprising here. If we actually want to take a closer look at the temporal scale separation, then you should take a look at the Fourier transform of your SDE. You just take the Fourier transform of both equations. You use some identities in the Fourier space. You actually find out that the power spectrum of both the temperature anomalies in the atmosphere and ocean depends on the stochastic forcing. Like I said, if you have stochastic forcing in one component, it will eventually get transmitted to both. And if you take the power of this, which is basically just the square modulus of this complex number, you find out that this gap in the power spectrum at high frequencies depends on the m. So this increases as m increases. So the rate of evolution of temperature anomaly in the ocean and atmosphere is relatively defined by this m, as we can just see from this graph and this expression. So if I run a simple sample free run for, say, a value of m equal to 10 and some a fiduciary amplitude of 1, whatever that means, we see, we can kind of visualize how the process works. So the atmosphere, as you see, is highly stochastic because of its because of its own forcing by the stochastic term, and the ocean kind of responds more slowly, and it has a smaller amplitude because of m as well. So you can actually take this 2 time series and you can try to calculate the cross correlations, the autocorrelation and the cross correlations, which is given by this function here. So the correlation between 2 time series given a lag tau is simply defined by this integral. So basically you take 1 time series, you kind of move it around, and you see at what lag you have the maximum correlation. And this will actually tell you, the peak of this function will actually tell you, how fast or how slow, again, one component is acting compared to the other. So when you actually calculate the autocorrelation and the cross correlation, you see what we already expect. The atmosphere has, the autocorrelation in the atmosphere falls very fast as you increase the lag window, which is what we expect because atmosphere is the fast moving variable, and the ocean kind of evolves slowly. But the important thing to note here is that because of m being not equal to 1, there is an intrinsic scale separation which kind of features here as a lag in the cross correlation. This basically means that the atmosphere leads ocean in the sense whatever happens in the atmosphere is going to affect the ocean later. So the ocean is going to catch up to the atmosphere in time, not right away. Yeah. Yeah, sorry. So now you can start asking questions. Okay, now I know that there's a peak of correlation at some negative lag time. What is this value? Is this value constant or does it have a variance? So you can try to run a number of samples where each sample gets a different realization of the noise f, so you can kind of calculate the intrinsic variance in this peak peak lag time. So you see that when m equal to 2, which means when the ocean and atmosphere are relatively evolving at the same time scale, this lag value it kind of tends to 1 to this side. So there's the minimum lag, and then you increase m, as you can see in these plots, 10, 30, 100, you see that the peak lag time also increases. And the distribution of this lag also increases. You can see that it's more skewed for higher m. So a little bit of algebraic manipulation with the matrix of C. You can see, kind of run some experiments, and you figure out that the mean of this distribution and the mode kind of depends on m and that of C. But the higher moments, which means the skewness of this distribution, depends on the off-diagonal elements, of course, as you would expect. So for our experiments, I'll mostly be considering m equal to 10, which is kind of, it doesn't really matter, m 10, 20. All it matters is that it encodes the temporal scale separation, which is what I'm most interested in. So on this one, I will run an ENKF experiment. Here, I just wanted to define what I mean by weakly coupled and strongly coupled DA. So weakly coupled DA is simply when you turn off the off-diagonal elements in your P matrix, in which case you have the normal Kalman gain in your individual subcomponents. So the atmosphere assimilates the observation from itself, and the ocean does it too, but separately. So that's what we call the weakly coupled. A strongly coupled DA is simply when these terms are non-zero. So your standard DA is actually a strongly coupled DA. And then you have the full K matrix, the matrix of the Kalman gain is given here. So we will run this experiment with an ENKF scheme. And this is just to, well, I should have actually put this before. So this is just to give you a visual representation of how the scheme works. I mean, this is applicable to all DA, not this experiment, just a graph I drew, a figure I drew a while ago. So you see that the atmosphere in itself is taking the forecast ensemble and the observation ensemble, and it's applying the process of analysis and forecast to it. And then it kind of keeps doing it as we know how DA works. And in the ocean, I've actually, it's the same process, but I've shown here is that the ocean is actually a bit slower. What it actually means, not slower, what it means here is that the observations in the ocean are not readily available as sparsely as in the atmosphere. So usually, let's say that the time stepping in the ocean is kind of more sparse than in the atmosphere, just for being more general and more realistic. So in the weakly coupling, this DA happens here, this DA happens parallelly, and the only information that these two components will share are during the step of the prediction through a flux exchange. The strongly coupled DA, in contrast, just simply as this process in the middle where you have the exchange of information from atmosphere to ocean and ocean to atmosphere and vice versa. And now the time stepping will play a role, as you can imagine. Now, because the time stepping if in the ocean is different than the atmosphere, you will eventually realize that how often you can do a strongly coupled update actually depends on both of them. Again, it's a very general case. For the sake of our experiment, we'll actually assume a very simple case. Yeah. Here I've taken motivation from the paper by Lieu et al. In 2015, two papers A and B, where they first proposed something called the leading average cross correlation. So this is basically designed to take advantage of the fact that that at any time t, my state in the ocean is dependent on the state in the atmosphere in the past. So usually, what we want to do is we want to kind of assimilate data not at the current time in the both subcomponents, but we actually kind of want to move in time and figure out what data is most relevant at what time. So this is one of the most one of the simpler and the first methods in this regime that was proposed by Lieu. So you can actually kind of summarize it in a way that you have kind of 4 parameters that your ENKF scheme is taking. It's taking what kind of operation that you will be operating on your forecast, what kind of operations you'll be doing on your forecast, what kind of operations you'll be doing in your observations, and in this and the data and the time between the two data the data between 2 times that you will be taking between T1 and T2. So in the weekly couple update, we don't perform any operation on any data in the past or the present. So it's kind of these all operators are null. It doesn't matter. In the simultaneous cross correlation, which is simply to say strongly coupled DA, is just another name for it. What it basically means is this operator is is a unitary operator, which means it only affects the current time, and it only takes the data at the current time. So it's basically just your strongly coupled DA. In the Langue method, what it does is we replace these operators by an averaging operator. So you will average your forecast in the atmosphere, as well as you will average your observations in the atmosphere, and then try to assimilate in the ocean. So basically take advantage again of the fact that the atmosphere is leading the ocean. So these operators act on both the forecast and the observations, and of course they take data from some time t back until some window time tau. So this is a very simple formulation, and once you do the NKF on this is a sample time series, and the DA procedure for a sample m equal to 10. I took a number of ensembles was 25. I started at 0, 0 as the mean, and some ensemble spread, some observation spread of the same order of magnitude. So my Kalman gain has some kind of, in between magnitude. It's not 0 or very large, and with 100 steps on the spin up. So we can see how it kind of works out. There's not much information to actually gain from here that you can actually gain here from the RMSE plots. So as expected, the first 100 steps are the spin-up steps. After that, the DA starts. As you see, it quickly converges. And you can see that the mean, but then the more important point that I want to emphasize on is actually the difference between the strongly coupled and the weakly coupled. So I will always be talking about the difference between the two as delta RMSE. So if you see delta RMSE, it basically means delta between the strongly coupled and the weakly coupled. So we see that the atmosphere actually gains by actually having a strongly coupled update, as well as the ocean, which is what we expect. We're actually, we're now taking all the information that has to pass through the subcomponents, and we're considering all of it instead of kind of only considering the diagonal elements in the P and discarding the off diagonal. So this actually makes sense. It's very consistent. One shouldn't be surprised by this. The more interesting thing happens when you actually start applying the Langue method. You start taking windows over the previous forecast or the previous observations. Here, what you see, I've taken a window size of 10. So what it basically means is that I do a strongly coupled update here, and then I wait for 10 more observations in the ocean, and then I take an average of the previous 10, and then I do my DA. So basically, I'm waiting for every 10 steps in the atmosphere, then taking the average of the previous 10, putting it all together, and making an update in the ocean. And in this, you will easily see, you will quickly find out that both in the atmosphere as well as the ocean, it's actually, the update is much better. The update is higher. So the strongly coupled is actually a little bit higher. The magnitude is minus 1.71, here was 1.58. So you're actually now sampling more correlations than you were before. And now you can start asking the question, a more broad question. So let's not consider one M or one lag. Let me just I can run this. It's a very simple model. It doesn't take too long. I can just start painting this M and tau plane. So the M and lag plane, I just start painting it, and I start running a number of ENKFs for each one of these pixels, and I see what comes out. Now in this picture, so this is for the ocean, and we are mostly concerned with the ocean because the project, my project kind of points toward more about tracking the slow component of so more the oceans, the long time predictions, not the small scale atmosphere, but most the ocean. So I'm mostly concerned about ocean most of the time. If atmosphere gets doesn't really matter to me. Ocean is what I'm most worried about. Atmosphere it doesn't mean atmosphere gets worse. It doesn't really, but if it gets worse, I'm willing to sacrifice some of the SNR from the atmosphere to actually gain some in the ocean. It actually has kind of a feedback effect as well, that even in the long term, your low frequency ocean components will also couple with the low frequency atmosphere, also sometimes the high frequency. So it actually is not that naive of an assumption. So what I do here is, so I try to paint this plane, and if you look at the ocean, you actually kind of see this feature where there's kind of this diagonal pattern here that as you move toward higher M, longer averaging windows give you a better update, which is what we expect. We should expect this. Higher the M, higher is the lag time, which means the more you average in the past, the more you assimilate the information which is useful. And averaging kind of filters out all the high frequency noise. So the high frequency oscillations in the atmosphere will get filtered out because of the averaging operator, and you only assimilate the low frequency component in the ocean, which makes everything better. And now and there are these patterns that I will actually describe a little bit more in detail. If you look at the RMSC and the spread, some people will, I mean, I'm sure I thought someone would ask me this question, that this spread looks like it's collapsing, so I'll just address the elephant at the start. The system is stochastically perturbed with a quite high amplitude at all times. So the spread kind of, the RMSC versus spread ratio never really converges to 1 uniformly. The mode is at 1, you can't really see it here, the mode is at 1, but you still have a lot of fluctuations where your truth is not covered by your ensemble. And this is because the model that I'm using is actually very suboptimal. It's stochastically forced at every step. So there's lots of noise that you're actually assimilating at all times. If you had actually done this forcing kind of more periodically, in the sense more spread out, you will see that this kind of, it doesn't happen. It uniformly converges to 1. In the Lieu et al. Paper, what they did was they actually did what they call a cross-localization, which means that every DA step, when they're making the cross update, they kind of deflate the update a little bit, because they know that the model is noisy, so I'm assimilating a lot of noisy observations, so they kind of ad hoc deflate it. And this kind of makes all the noise features that you were seeing before in this M-tau plane kind of go away, but this is of course expected, because they kind of reduced their SNR, they kind of cut out the information that they were trying to assimilate in the first place. So it seems kind of somewhat counterintuitive to actually do this process, that you kind of first want to maximize the SNR by taking a lagging window, and then you kind of say that, okay, it's too much SNR now, I have to cut it out because it's giving in too much noise. So it's not necessarily a problem with the process here of the ENKF or the DA, but it's actually something to do with the model. So if you actually have like I said, a sparser stochastic forcing, then this wouldn't happen. But this is just to show the effect of what the cross-localization does actually. So you have this inflation and problem even in the strongly coupled DA, but it's actually not as straightforward as you will assume in the weakly coupled, because then you have to take care, your localization in one component might not be the same as the cross-localization, so you may have to have, kind of an adaptive or kind of non-uniform, non-homogeneous inflation or localization. Now, one could also start asking questions about this pattern that you see here. You see that it's kind of a periodic oscillations beating against each other. You wonder why that is happening. And if you look at the Kalman gain in the Fourier space, so this is all the Kalman gain components. These are the two diagonal components, and these are the off-diagonal ones. And this is just the Fourier spectrum of it. So if we actually take the Fourier spectrum for the case of m equal to 10 for the SIMCC method, which is the normal strongly coupled, and the leading average, you see what the windowing does. It actually gives your system tiny impulses at all times, which manifest in the frequency space as is excess power and low power around a mean which is defined by the weakly coupled. So the difference between the strongly coupled and weakly coupled is simply the difference of the sum in Fourier space. And you can see that as you take more lagging windows, more of these oscillations kind of start fading in and out. So there is kind of a residual integral left at the end, which kind of gives you this oscillatory nature. So this kind of tells you that these oscillations that you see in the background, they're actually kind of not real. They're just kind of a residual effect left from the DA. And so the main thing that you should be focusing on here is kind of this diagonal feature where you see that for higher M, you should actually take longer correlations. All right, so to conclude, so what I did was a simple experiment, and so through the process of doing this, I realized what I'm doing is I'm just choosing an operator which kind of works well for this model, because the model is a certain way. So in this case, the averaging operator is actually a linear operator which operates on some samples in time, which each has some weight, but it's linear, and the model is also linear. So this kind of helps, which means the set of possibilities that you start from and the linear combination of these possibilities also lie in the same probability space as the first one. So this operation kind of, you don't have to think too deep about saying, okay, can I just add the gain from a model which is what it is and the gain from an average of the model? Can I sum it? And for this case, it's actually very easy. Yes, you can sum it, but once your model gets nonlinear and you realize that you could have much more complex correlations, not just a simple averaging in the past, but you could maybe forced to take, for example, point-wise samples in the past instead of taking an average. So your choice of operator depends on the model, and it can get more complex as the model gets complex and complex. And then you will eventually have to start asking the question: can I assimilate? Can I do a DA on a model the way I do it, and then do a DA where an operator is acting on the model and the observation in a certain sense, and then sum the two? It's not necessary that at all times these two spaces are additive. They can't be at all times. Sometimes you may have to take more complex forms. So this is basically what I'm going at eventually, that if I start with a more complex model now, then I will start realizing that I will need a better operator. I'll need a different operator to operate in the past. And this becomes more and more complex if you include the scale separations, like I already said. So if your one counterpart is moving much faster or slower than the other counterpart, then you don't want to, first of all, you don't want to do the assimilation step too often, because then you will be adding in a lot more noise, and hence kind of masking the low frequency variability. So your optimality of your DA will depend on a number of things now. How often your DA, how the scale separation, and then you have the spatial separations as well. I'm not now considering the spatial localizations. I mean, I'm considering everything. Information is exchanged in space, like with the speed of light, Nothing happens, but it's not necessarily true. So we need to make the model more general, more realistic, more complex, of course. And the practicalities, I can't see myself here, but I didn't make any comments on the computation cost yet, because it's a simplified model. Once we get to more realistic, complicated models, which we have to run in real time on real CPU cores, I might have to start worrying about how much energy and money I'm spending. And the inflation and localization is, like I already said, it's not really trivial. It's not straightforward. You have to think a little bit. And that's it. So let's make it stronger.
Thank you very much for this very nice presentation. Some comments, questions?
So in the real world, your M is going to be fixed by how the atmosphere and the ocean are coupled.
Yeah.
So when you're using your lagged covariances, you get to choose what lag window you take. But if you're interested in the forecasting problem, you're going to necessarily not be able to make that lagging too long, I think.
Well, yeah, of course.
Because you have to get your forecast on it.
Yeah.
So given that you've shown that it's more optimal to have a lagging window which is comparable to your M in some relationship, how much do you lose if that is really short?
How much you lose if your M, if
compared
compared to M, your lagging window is very short?
When you know it should be longer.
Well, it depends. The thing is, if you actually approach the same order of magnitude as M, for example, if M is 10 and the peak lag time is 20, so as you approach 20, you kind of gain very fast. But after 20, now it depends how far. For example, you just need to actually just see this plot, the cross here. So you basically need to see how fast or slow this cross correlation is kind of decaying on the other side. Basically, that answers the questions. For example, so in this case, the peak is at around 20. So if I start going toward 20, I will first gain a lot, and then my gain will become smaller and smaller. Yeah, and a very interesting case of this is if you actually do this for m equal to very large value, just on the same line of question that you asked, this spectrum kind of just like flattens out. So this cross correlation increases up to 20 and then kind of flattens out, and then all the noise factors kind of then make your peak of your lag kind of disperse at very large values. So at very large values of M, you will gain until some point, and after that it will become irrelevant. It doesn't matter what you do anymore.
Other questions, comments on the work? If not, thank you very much again.